For the chapter 27, we have to talk about the molecular crystal and the structure and properties of ice. There should be two things we need to memorize, the molecular crystal and then or the structure and the properties of ice. But the 27.3, actually in the new textbook, we don't have it. It is the structure and properties of carbon-60. If you want to know more about this topic, about carbon-60, you may refer to the older version of the textbook. First of all, talking about the molecular crystals. The molecular crystals must be a solid as it is a crystal. So they have an ordered arrangement of molecules called molecular crystal because they should arrange in the order manner. Examples of molecular crystals include iodine, ice, or table salts. Sorry, table sugar. The table sugar is so close. First of all, introducing the iodine crystal first. Iodine molecules are also held together by weak van der Waals forces. Iodine molecules are packed closely together in a regular pattern. So they must be starting with a regular pattern first. You can see actually the first layer, in fact, it is repeatedly occur. And then it's, in fact, it is the third layer. So the first layer here is repeated at the third layer, then it repeats itself. That is the second layer will be the fourth layer actually. So they packed it closely together in a regular pattern. It is the iodine crystal. The same case will be the dry ice. Now, it is not a must to be all of the molecular crystal having such pattern. However, just luckily, the dry ice and the iodine share the same case. So you can see this one is repeatedly occur in the third layer again. So the carbon dioxide crystal, they are held by the weak van der Waals forces. But this solid line, in fact, there are no ionic bond at all. However, they just got the weak van der Waals forces with each other, but they can still pack it together closely in solid states, that is the dry ice, with the regular pattern. This is the carbon dioxide molecules, but it forms the van der Waals forces, attract with the van der Waals forces with the neighboring carbon dioxide molecules. Although it is weak, but in a very, very low temperature, it can form the solid dry ice. The molecular crystal in ice and table sugar are shown here. The next one we need to go into the detail is about the structure and properties of ice. The ice, the freezing of the water here. When you take a look, at room temperature, the water, it will vibrate strongly. However, as it is going lower and lower, then it will only vibrate not such strong. So you can see, finally, when it is really, really cold, you can see here, it seems that a hexagons occur. So this one, the structure of bonding of ice, that for this case, it is not a three-dimensional diagram. It is just a two-dimensional. If we think about the tetrahedral arrangement of the water, because the shape of the molecules itself is tetrahedrally arranged. So when we formed ice crystal, the hydrogen bond must be the ice crystal. That means they are solid. They have to get closer and closer with each other. They have to form as the right orientation. That means the tetrahedral shape, again, it comes out. So the hydrogen bonds, when they form, the four hydrogen bonds with four neighbor water molecules tetrahedrally, 1, 2, 3, and 4. So each water molecule can form total of 4 hydrogen bonds with 4 neighbor water molecules tetrahedrally. But each water molecule can form 2 hydrogen bonds with neighboring water molecules on average. Now, if you say describing one molecule, it can form 4 hydrogen bonds. However, it is not on average because on the edge side, it should be no hydrogen bond at all. So on average, it's just got 2 hydrogen bonds with neighboring water molecules. So it should be forming as it is tetrahedrally arranged. It should be forming like this way. So again, you may see the hexagons coming out. The hexagons that formed it, and then, it will give some empty space here, some empty space instead. But the oxygen atom of each H2O molecules forms hydrogen bonds with 2 hydrogen atoms of nearby H2O molecules. But the 2 hydrogen atoms of each water molecules also form hydrogen bonds with oxygen atoms nearby the H2O molecules. So in the ice, the tetrahedral arrangement of water molecules repeat again and again, resulting in a regular network structure. But because of the empty space there, and then you can see the water molecules, there are a lot of empty space, we say that the structure has open structure. So in liquid water, hydrogen bond still exists between molecules. However, they form and are broken continuously. There is no regular packing of water molecule. So when we take a look here, it's found that the hexagon arrangement of oxygen atom in ice. So the empty space here, it forms a hexagon shape. That's why the hexagonal shape of snowflake reflects the structure of ice. Compare the structures of diamond, silicon dioxide, and ice. Actually, they are very, very similar. The diamond, you can see again, it is just similar to the ice one. However, the only difference is in the diamond, in the silicon dioxide, it is just the covalent bonds exist. While in the ice, apart from covalent bonds, it contains hydrogen bonds. So in fact, it is the weak intermolecular force. So it is easy to break. However, due to its regular pattern, so it also have a good refractive index as well. The property of ice. So most substances have higher density in the solid state than in the liquid state. This is what the particle theory mentioned. Because the solid state, they should pack well, while in the liquid state, it should pack loosely. For the case for liquid paraffin or the solid paraffin, it is the case. If we put the solid paraffin into the water, it will sink. However, sink into the liquid paraffin. However, if we put ice, instead of sinking, it is floating on the water instead. We can show that again, solid paraffin, the solid particles pack closer. So the solid paraffin is denser than that in liquid paraffin. However, that is not the case for the ice. Why is it so? In ice, water molecules are arranged in an orderly manner, in an what we call the open structure. The open structure, that means they have the empty space. Because of the extensive hydrogen bonding between them, there is an open structure in between the water molecule they arranged. In this structure, water molecules are further apart than they are in the liquid water. Thus, they take up a larger volume. But when ice melts, the open structure collapses, they can go closer. So the water molecule can pack more closely together with each other because they can move freely for the water molecules. So the water molecule in ice, so it is not move freely. As a result, they have to stay rigid there, and then it is tetrahedrally arranged. It must be tetrahedrally arranged, so open structure there. But when ice melts, the open structures collapse. The hydrogen bond in water make the empty space there. In this open structure, water molecules are further apart than the liquid one. So once it's collapsed, it can even get closer with each other. So that's why we can see the ice can float on water instead, because ice has the open structure, the empty space make it having a lower density. That's why in the cold weather, ice forms a layer on top of a pond. Ice acts as an insulator for the water beneath. So that is here. Water, like water is a almost unique among the more than 150 million known chemical substances. In that, is solid, is less than water, the liquid one. So once the ice formed, then it has the insulating effect. It cannot affect the bottom. As a result, the bottom, the fish can still move here. It will not die. Why does ice flows on water? You may refer to this YouTube later on by yourself. The melting point. The melting point of ice is 0 degrees Celsius. Comparing with the substance with similar relative molecular masses, for example, methane, ammonia, and water, actually the melting point is the highest, just because the hydrogen bonds presence in water, while it has more extensive connection or more extensive hydrogen bonds formed between water than the ammonia. When ice melts, a considerable amount of energy is required to overcome some of the hydrogen bonds between the water molecules. As some hydrogen bonds are broken, the open structure of ice collapses. So, the presence of extensive hydrogen bond between water molecules in an open structure of ice make the open structure of ice. Because of this special structure and bonding, ice has a lower density than that liquid water and relatively high melting point. For the carbon, now I just want to mention one of the wood, which is called allotropes, because you will find that in some of the past paper. So we have two forms of carbon. One form is diamond, one form is graphite. In fact, diamond is tetrahedrally arranged, while graphite, it has weak van der Waals force between the layers. So the layer structure, while this one is tetrahedrally arranged. So we say that we have two allotropes. The allotropes of carbons means they are same element carbon, but they are having different form or different way to pack it. So anymore, actually, there is another one, which is called C60. C60 is a fullerenes. They are molecules